So welcome back to the fourth part of the first week, where we are going to continue our conversation from last time about scheduling classes. So let's spend a moment recalling the problem. We are given a collection of classes which happen to be dance classes hosted by a dance academy that runs these classes every Saturday, and the classes are slotted between 8 a.m. and 8 p.m. and they have a timetable that looks like what you can see on your screen here. And the only rule that they have is that you cannot register for two classes which are overlapping in their timings. So for example, we have the ballroom class which begins in the morning sometime and ends around 2 p.m. and we have hip hop starting at 1 p.m. and going all the way up to 3 p.m. or so. These are two classes that you cannot sign up for simultaneously because they overlap in their timings, and we will just say that they have a conflict. So what we are looking for is the largest collection of classes that are mutually conflict free so that you can actually register for all of them and explore your newfound hobby of learning dance as much as you can. So let's take a look at the strategies that we considered last time. So we said we could try picking the class with the fewest conflicts. And then after making this choice, of course, we would have to remove all the classes that conflict with the chosen class and repeat this for as long as we can. And it turned out that this didn't work. We also said we could try to pick the shortest classes first, and that also did not work, as we saw with a simple example. And finally, the third thing that we proposed is to pick the earliest class first, which is to say that we wanted to pick the class that starts the earliest first. And we saw that that could fail quite dramatically as well. What we did conclude is that none of these strategies actually work, in the sense that there are examples where they would fail to give the optimal answer. But on the other hand, we proposed a different greedy strategy, which basically suggested picking the class that finishes the soonest, or the class that finishes the earliest first. Give that your priority, and then do the same as with the other strategies, which is to say proceed by eliminating all conflicting classes and moving on and repeating this procedure for as long as is possible. So let's try this out on the example that we have here. So among all the classes, it would appear that tango finishes the earliest. So that's what we are going to pick in our solution. And we see that we have freestyle and Bharatnatyam conflicting with tango. So we want to eliminate those from our consideration. Now, among the remaining classes, which one finishes first? Well, it would seem like we have ballroom, which finishes the earliest. So we are going to go and make that our next pick. It might look like tango and ballroom conflict on the edge. Probably it's not clear from the picture if the end time of tango is the same as the start time of ballroom, but the convention that we are going with here is that that's not an overlap. You will have enough time to change between classes if they just overlap on the edge, so to speak. So I'm going to go ahead and make this choice. But ballroom has a clear clash with hip hop, so we are going to have to eliminate that from our consideration. And among the classes that remain, we have, I think, Odyssey finishing the earliest. So we are going to go and mark that for inclusion in our collection. But Odyssey definitely overlaps with salsa and Kathak. So we get those out of our way now. And then among the remaining classes, the one that finishes the soonest is Bollywood. So we sign up for that one. and that eliminates ballet and contemporary. The clash there is quite clear. So we've ended up with a collection of 4 non-overlapping classes, although it's a pretty tight schedule considering Odyssey finishes when Bollywood starts, and it also starts when ballroom finishes. So that's going to be a few back-to-back classes. You can probably experiment a bit to find schedules that have 4 classes but are not so tightly packed. For example, you could switch out Bollywood with ballet to create a bit of a breathing room towards the end. But nevertheless, this would be the output of our most recently proposed greedy strategy. Of course, it's not obvious that it works. In particular, even if you have convinced yourself that in this example you cannot do better than 4, it still doesn't mean that this algorithm is guaranteed to work on all instances. It may have just lucked out on this one, right? So what we certainly need is an argument supporting the correctness of the algorithm on all conceivable instances. Before we get to that, let's just write down the algorithm in pseudocode, and you're welcome to try implementing this in your own time, although it's not really required for any of the assignments. It's one of those algorithms that's not difficult to implement, and it could be fun for you to try it out. So to begin with, we are going to sort the classes by when they finish. So the classes that finish first come up front in this sorted order. We're going to initialize a couple of variables. Count will help us keep track of how many classes we have picked so far, and X is going to be our actual collection of classes. So we initialize count to 0 and X to the empty set. Now, while a class is still available, we are going to add the first class to our collection and remove it from the instance. So the first class is the first class with respect to the sorted order. And let me refer to this chosen class as C so that I can refer to it in the next line of code. What I want to do now is to eliminate all classes from the instance that have a conflict with C. Since we have committed to register for the class C, we cannot simultaneously register for any other class that has a conflict with C, so we might as well get rid of all of them. After this, the while loop takes over, and it's going to continue adding classes that finish earliest and eliminating conflicts for as long as it's possible to do so. And we've already run this algorithm on an example, so let's just pause here for a moment to make sure that we agree on the mechanics of the algorithm, how it works. And if that's clear, then you can join me for the next part of the discussion where we try to prove that it actually works. So before we get to the proof of the main result, which is that this algorithm is optimal, I'm going to prove a lemma which will help us in the subsequent proof. So the claim that this lemma here is making is that there is at least one optimal conflict-free collection of classes that includes the one that finishes first. So we are not saying that every optimal collection is obliged to pick the class that finishes first, but there's at least one. And we will see how this optimal solution, which makes the same choice that greedy does for the first class, will help us anchor the argument for the correctness of greedy in just a minute. But before we get there, let's actually see how we can prove this lemma. So let's identify the class that finishes first. Suppose it's this interval that's shown in blue here. Now pick any optimal solution you like. Just come to me with your favorite one. And if your optimal solution already has the blue interval, then there's nothing for me to do because it already has the property that I'm looking for. On the other hand, suppose it does not have this class, then notice that it must have some class that conflicts with this one. Because if it doesn't have any class that conflicts with this class, then I can simply add this class to your solution, and that would contradict its presumed optimality. So let's stare at a class in the optimal solution that's conflicting with the one that we have. Now notice also that you cannot have more than one class in the optimal solution conflicting with the blue interval. And the reason for that is that the optimal solution itself is a collection of non-conflicting intervals. So the only way that you could have another interval that conflicts with the blue interval without conflicting with the red interval is if the interval looked like this. So it has to come into the blue interval, but it has to stop before the start of the red class. But think for a moment why this is not possible. Well, this is not possible because the blue class is the class that finishes first. And if we did have an interval like this one, then it would mean that we have another class which finishes before the blue one does, contradicting the way that we defined the blue interval in the first place. So we have this situation where your optimal solution has exactly one interval that conflicts with the interval of interest, which is the one that finishes first. Now I'm going to modify your optimal solution by simply swapping out the blue and the red intervals. Notice that by removing the red interval and adding the blue interval, I don't change the value of your solution. You take one, but you also put back one. So the number of intervals in the optimal solution remains unchanged. Therefore, this new solution is also optimal. Now, we just have to make sure that it's in fact a valid solution. But notice that because the blue interval ended before the red one did, it's not going to conflict with anything else. Because for any other interval in the optimal solution to conflict with the blue one, it would also have to conflict with the red one. I hope that that's clear, and you can see that therefore all of these arguments combined give us a new solution which is also optimal and which contains the interval of interest. So that proves our lemma, and we are done at this point as far as the lemma is concerned. Now let's get to the main theorem where we want to say that the greedy schedule is in fact optimal. And how do we go about showing this? Well, there are several ways, and I will show you two different approaches to this proof. The first one is going to be by induction, where we use the lemma that we just proved, and the other one is going to be a more structural argument involving the greedy choices themselves. So first, let's do the proof by induction. Let's assume that we have an instance with some n intervals, and let the induction hypothesis be that the greedy algorithm does the right thing on any instance that has fewer than n intervals. When n is 1, there's practically nothing to prove, so that will count as our base case. Now, in general, suppose you have a collection of n intervals as your input, and once again, let's bring up the interval that finishes first. Now, remember that there is an optimal schedule that contains this interval, and we are going to bring that up in just a moment. But before that, notice that this interval partitions the remaining intervals into two parts. The first part is all of those intervals that conflict with this one, and the other part is all of those intervals that do not conflict with this interval. So you have broken up your instance into two portions, so to speak. The pink intervals are the ones that conflict with the blue one, and the gray intervals are the ones that don't. Now let's get back to the optimal solution that is guaranteed to us by the previous lemma. Remember, what's special about this optimal solution is the fact that it contains the blue interval C. That implies that it cannot contain any of the pink intervals, and all the remaining intervals must be among the gray ones. So why is this useful? This is useful because it tells us that the value of opt restricted to this subinstance is k minus 1 if k was the value of opt on the entire instance that we started with. Now what we can do is apply the induction hypothesis to the set of gray intervals where we know that the greedy solution is optimal. That's what the induction hypothesis gives us. And because we know that opt is k minus 1 and we know the induction hypothesis to be true, we know that greedy when run on just the gray intervals is going to give us a collection of k minus 1 conflict-free intervals. But now we can just add back the blue interval to this collection, and now we have a collection of k intervals that are conflict free and that are optimal. So I hope that that argument made sense. Essentially, we are combining the structural leverage that we are getting from the previous lemma with the power of the induction hypothesis. You should try to convince yourself that if you didn't have the handle of the promise that there is an optimal solution that extends the choice of C, then just using the induction hypothesis on its own would not have been enough. However, let me also walk you through a slightly different proof that you might find more intuitively appealing. So let's step back and take a look at all the choices that are made by the greedy algorithm. They're highlighted for you in blue here. And let me now just drop a perpendicular from the finish times of all these chosen intervals. Now I would like to claim that all the remaining intervals overlap these perpendiculars, at least one of them. Why is this true? Well, let me try to draw an interval that avoids any of the pink lines. That means that it must sit inside the region between two consecutive pink lines, which means that it probably starts somewhere here and it must end before we reach the next pink line. Take a moment to see why this is problematic and why such an interval cannot exist. Well, you might have guessed that such an interval cannot exist because of the validity of the greedy choices that we have made. So, because the greedy algorithm chose to pick this interval, we know that at this stage, all the intervals that were available finished after this pink line, which means that we couldn't have an interval that looks like this. Okay, so why is this useful? Why is it useful to know that all the remaining intervals actually overlap one of the pink lines? Well, that's because this essentially gives us a partition of all the classes into k buckets, where I'm using k to denote the output of the greedy algorithm. And what's special about the classes that sit together inside one bucket? Well, these are the classes that overlap a fixed pink line, a fixed perpendicular, which means that they're all mutually overlapping, right? Because they all are active at that point of time. So it's not possible to pick more than one from any of these buckets for any solution. So any solution is constrained to picking at most one interval from these buckets, which means that we know that opt is at most k. On the other hand, the greedy outcome actually has k intervals, which means that greedy actually achieves the best that you can hope for, which also implies that greedy is optimal. So I hope that these two proofs gave you some intuition of a formal kind for why this particular greedy choice works. In the practice assignments, you will have a chance to explore many other greedy choices, and you'll have a chance to think about which ones of them work. So I hope you enjoy thinking through those, and I look forward to discussing those problems with you. In the meantime, this closes the chapter on scheduling classes. What we are going to move on to next is another very interesting and classical problem called the stable marriage problem, which is a wonderful example of a natural greedy strategy actually working out to give us a very deep result. So I'll see you then.